Welcome to this lecture from the course on thermal building physics, the lecture on transient heat transmission. It has several parts, and this is the part where we talk about analytical solutions for finite and semi-infinite bodies. It links on to a start we had with some lumped analysis that I will talk about. But now we're going to calculate how heat is transmitted into our walls or bodies, as we try to illustrate here. Temperature profiles, but also a little bit looking to possibly also heat flows and such. So as we start the lectures, we talk about this general heat conduction equation, a parabolic differential equation, where we should find the temperatures as they are functions of time and space, t and x. So we need for that, we need a thermal property, which is the thermal diffusivity of material in which we have our heat conduction to take place. But this equation, it's not straightforward to solve, so there's a little bit, that's why we have this lecture, about how to solve the equation. So that was set up also from the talk about lumped analysis, a problem-solving strategy, and the initial part of the lecture, which we have done already when we come to this here, we talked about lumped analysis. But also there are certain solutions for, yes, for semi-infinite bodies and for finite bodies, and I'll come back to explain what we mean by that. And then we also consider the boundary conditions, if it's the surface temperature we know, or the ambient temperature that surrounds the material. And also we have solutions for certain heat flux boundary conditions. And further on, if it's even more complicated, in the end, perhaps we have to go to numerical solutions, as it says in the bottom here. But here we have the lecture where we'll talk about the temperature entry into the material. So that's really this kind of solutions we're looking to here for this lecture here. We'll show some analytical solutions, formulas essentially, but also we will show later, or as we end, some chart solutions that you may also adopt in a few of the cases that we talk about. So to set it up a little bit systematically, we should first of all categorize what kind of situation we are dealing with. And the first I'm going to talk about is the semi-infinite body for a fixed surface temperature. So to cover the different situations I'll talk about, I've made this small table over here. So right now the cross I'm going to make is that we talk about semi-infinite bodies and fixed surface temperatures. So this is what I'm going to talk about first. Just to explain to you what I mean by semi-infinite bodies versus the finite body. If you consider this to be a wall with a certain thickness from the left to the right part of the wall, then it has a certain thickness, of course. That's finite. But you could also consider a situation where you have a surface on the left-hand side, and then, and that's a little bit superficial, but if there is no end to the material as we go to the right, it just projects infinitely. That's the semi-infinite body. It's superficial, yes, but for mathematical solutions to what we're going to show you today, it's easier to with such solutions. So that's actually our starting point, despite of the fact that the case is somewhat superficial. The other thing is about what is the exposure, and that's about what kind of conditions we know at that surface. So is it the surface temperature or the ambient temperature in the air, for instance, next to our material? Or the last case, with the surface heat flux, we have heat flux coming in. So that was a little bit more explanation of what we're going to talk about. And now let's get started. So in that case here that we have this semi-infinite body where the surface is a temperature that suddenly changes, then we have solutions. So that means we have an initial condition where everything in our material is at a certain initial temperature. And then suddenly at time zero, then a new condition arises where we get at the surface another temperature, the surface temperature Ts. And then if you're just infinitely into the material, then you still, at such a far distance, you will always have the initial temperature, but that's also infinitely far away. So the question is, how does the temperature develop in between as after this temperature, surface temperature has been exposed on the material? So here's a little bit of graphic, how it goes. So initially we're down here, initial temperature, and then we have suddenly a surface temperature to arise, and then we're going to look for those temperature curves. So here is the equation which you just have to accept it, if I may say. So that's a little bit a matter of identifying the case that you are dealing with and then adopt the proper equation. So this is the equation that tells us the temperature at location X at time t in our material, depending on those surface and initial temperatures we just introduced, and then this function where you insert the location X and the temperature, and again the thermal diffusivity of our material. But you have to adopt this formula here, this equation, our function, the error function, ERF, if you know what that is, because that is actually a standard function, also like other functions you might know, exponential, sine functions, and so forth. It's a function that comes out of probability analysis also. It has a counterpart, which also we sometimes use in our equations. So here we see the same equation, but with our counterpart, ERFC, the complementary error function. Here is the definition of the error function. Just to talk briefly about it. Starts at 0, goes towards 1, depending on the argument that you pass to the function. So that's the function we need to use, and again, the mathematical definition of it. The complementary error function is the same, but it's only 1 minus the error function, so it goes the opposite way as it develops. You can look up the values for the error function in tables. You can also make approximations using Taylor expansions. And the Taylor expansion is good when you start from the beginning for ERF, so the error function. So it covers the beginning area with reasonably good accuracy for engineering purposes. You could also look to an asymptotic expansion approximation for the complementary error function, which will give us good values in the range for when the argument is, say, bigger than 2.5. That's where we are very close to 0, but not exactly at 0. And that's actually a point we're going to talk about a little bit later also. Because now let's go to the next case that we have in our table over here. So now it's the convective heat transfer coefficient that tells us about heat transfer from the ambient conditions around the material to the surface, and then we have heat flow into the surface after that. That can also be illustrated over here. So now again, as I said, it's not the surface, but it's the ambient temperature that changes. So that's part of the heat transmission, and then heat transmission into our material. Okay, so we have an equation. Again, you have to accept, identify. It starts the same as we had before with the complementary error function, also the same argument, but then we have to subtract a little bit because the heat flow is slower since it has first to come to the surface of the material. And that looks a little bit more involving mathematically, you might say. So we should insert, again, the location x, and this is time t that somewhat fits in this equation here. But that's something, it's a mathematical equation. You can just solve it. But again, using the complementary error function, and in this time also the exponential. Things that you can find, for instance, in Excel programs, Mabel, other places. I'll just elaborate a little bit on this because there are a few complications, you might say, to it. I just identify some of the arguments that we pass to the exponential and to the complementary error function, and see that I abbreviate them. I call them argument 1, argument 2, argument, it's actually argument 2 coming again, because here we have the same in those two places, only here we take the square root of what we had before here. So this is actually the square root of argument 2. And then our third argument we have here. Just for abbreviations, renaming of the things, because there is an issue with this. When we calculate this, we have an exponential, and if, for instance, say A2, depending on that time and location where we are, for large values of some of those variables, the exponential as we take may tend very easily to infinity or becoming a very large number. But also when we take the complementary error function, for large arguments, that was the function that tended very close to 0. So in principle, for large arguments, we may risk multiplying something which is close to infinity with something that's close to 0. So what would become the result? A very large value, a very small value, we don't know. Perhaps it's a value somewhere in between. So to solve that, then we can use that asymptotic expansion I showed you before for the complementary error functions for large arguments. Here's the equation to be used, just for repetition from one of the previous slides I showed you. So when I insert values from that, it's a little bit involving. You can check me if I've done it correctly, but then it leads to this equation I have down here in the bottom. Rather complicated, you might say, but the interesting thing is that this notion about something with the exponential that tends to infinity, the complementary error function that tends to 0, where does it lead? Let's see if something eliminates here when we have inserted these approximations. And actually, this exponential is eliminated by this over here. And everything else what's left here is something which is neither close to 0 nor close to infinity. It's actually some real good numbers that are somewhere in the mid-range, you might say. So here's a trick how to calculate and to use our equation in cases where we have large times or locations x and t we insert in our equations. That was just a trick, but just to help you a little bit in the guidance of leading through using the equations for different cases. Next case we should talk about is the case of having convective heat transfer at our surface. So this is this part we can now cross in our small table over here. And that's again our material. It's semi-infinite. We have a surface heat flux coming in, so that could be, for instance, to represent solar gains, solar heat flux on a surface, things like that. Could also be night cooling if it were a negative heat gain. So such influences will also cause a temperature increase, and that will develop over time and depending on the depth in the material. So again, we just have a formula. Here's the formula. Also mathematically not so complicated, but again, using the complementary error function. So I guess you can use it. Just identify the case, and then you can calculate temperatures versus x and t as before. So that was enough for that story, and that was enough for the talk about semi-infinite bodies. Let's make it more reality. Let's make it now a finite body with a certain end on both sides of our material that we study. And the more we come to reality, a little bit more involving our numerical solutions mathematically. Not so bad, but you just have to keep it straight to know, to calculate this summation here in the formula here. Now we have an exponential and cosine function. It's something that you can, I guess, easily find with your tools and find solutions for. The case is the finite body. So again, initially we have the initial temperature in all of the material, and suddenly at time 0 we have a rise at the surface temperature. So it goes to Ts. So that means over in our table here we are now covering the case of a finite body with suddenly another fixed surface temperature on our material. Well, you can go in, you can make that summation, so that's something you can easily do. I can also write it a little bit differently, but just to help you on all the terms it takes to add up. But when you try it, you will find that very soon the terms tend to become very small. So perhaps you need only 2, 3, 4, you can try it, of those terms that have any significance for the final result in the solution. Then you may be able to draw curves like this, which tells you that initially we have a temperature up here. Suddenly the temperature at the surface drops to a lower value, and then you can draw curves depending on time, here plotted versus the Fourier time, the Fourier number, as the temperature goes down and seeks into the body of the material as such. So that's just an illustration of what you're able to do now. The last thing I'm going to talk about is the case where we have convective heat transfer over the surface of our finite body, of our wall material, if you will. So this is what we will cover. I may already today say that I will not talk about heat fluxes on the finite body. So the last case I'm going to talk about is this here, the finite body with the convective heat transfer on the surfaces. And there are a little bit some cases we can use. We can also refer to what we talked about in the beginning from the lecture that comes before this, where it was lumped analysis. So if the BO number is less than 0.1, you're simply referred to an assumed lumped analysis, which means that all temperatures within the body of the material are the same. But for larger BO numbers, but for small times, well then, if the material is finite or semi-infinite, the temperature profile has not developed very far into the material, so then you can use solutions for semi-infinite bodies, as we talked about before. But for finite bodies, the real case, for Fourier numbers not so large, so times not so large, well then there are some accurate solutions that I'll show you on the next slide. If the Fourier number is bigger than 0.2, then we can have an approximation to the accurate solution that we have on the level 3 here from this problem-solving strategy. So here is our equation that gives us the solution. So again, the temperature at location x and at time t, as it should say up here, is according to this formula here. You have to take the sine function of zeta n, and zeta n is a number, it's a coefficient we have to find a set of, so zeta 1, zeta 2, zeta 3, etc. for all of them. And then comes here in the cosine term, we have the location x where we are in our body, which is the distance from the center of our material. So we have to find those zeta values. So those are the roots, and there are a sequence of them, as I said before. They are the roots to this equation where you should take the cotangent of zeta should be equal to zeta divided by the BO number for our problem, which we always have to calculate. Let me just explain what is meant by these roots here. And this is a little bit old graphics which I've copied. We show a plot of the cotangent function, so it's a repetitive function that comes again and again for every pi we go out of the abscissor axis here. So that was the cotangent we have plotted here. That should be equal to that line, zeta divided by BO, as I had on the other slide, the previous slide. And where they have intersection points, that is where we have the so-called roots. So the roots are here. So this is zeta 1, zeta 2, zeta 3, and you can expand and find the next ones also. That means that in this case, if I may draw it over here on the whiteboard, I would say that zeta 1 is equal to 1.1, it looks. Zeta 2 is equal to 3.7. And zeta 3 is equal to 5.7. And you can project and make the next ones yourself. So those are the coefficients that we need in order to use our equation. The rest would just be to insert in our equation and simply use it as such. So that's the solution for that. And that also completes this talk that I chose to bring with me today. So here is a repetition of this, except to say that we have also, as I promised, we have charts where you don't have to use the formula I just showed. So as a very final part is that you can use these charts, but then you have to find the BO numbers. Also, as I said, you very often need to calculate them. So with a proper curve representing the BO number, then you can go in here and find the center temperature, that is the temperature in the middle of the body that you're calculating for. On the abscissor, you should insert the time as a Fourier value, so according to the definition of the Fourier number. And then you can find the temperature in the center as a relative temperature compared to the temperature in the ambient air and the initial temperature we had in our body. That will give us the center temperature. Well, you might be interested to know the temperature in other points than in the center. And then there's another chart that will tell you the relationship between that temperature and another location compared to what is the center temperature and the ambient temperature. Again, a relative number between 0 and 1. And to read where you are, you have to insert that location, x over L. L is the characteristic length of the material, which is half of the thickness of a double-sided exposed material. And x is the distance from the center of the material. So for this material, capital L would be half of the thickness of the material. And x is the distance from the center where we are. So you go in here, find the proper curve, and then you insert the BO number down here on the BO, on the x-axis of the diagram, and so you can find that temperature, how it is in relationship to the center temperature. Those are the charts, and then you don't have to calculate. You can simply insert and read it as accurately as you can with such charts. Okay, guys, that's all I wanted to bring with me today here. So I hope you could appreciate and understand these ways to present this part of the lecture here. Thank you for now.